and liftoff.
Hello, and welcome to this new episode of Kleos Insights. Hello, Federico.
Hi, Rami. I'm delighted to be here.
Before starting the technical questions, can you tell us a little bit more about yourself? Where did you come from, and why have you decided to join Kleos Space?
Sure. So I'm a space systems engineer. I moved to Luxembourg right after graduation. I took my master degree, and you can understand while studying, you always try to find an application which is serving to a greater good. And I was actually able to find one thanks to Kleos. Kleos gave me the opportunity to contribute in geolocating cooperative and uncooperative target, contributing to maritime surveillance, and also defining maritime applications as a sort of Earth environment protection.
So you're definitely in the right place, because what Kleos does is geolocating RF transmissions. So we're using a spacecraft to passively geolocate RF transmissions that belong to illegal and hidden activities. And unfortunately, these illegal activities occur in different regions in the world. My first question is, what are the oceans or the seas that are covered by the Kleos constellation, and how you define a coverage, basically, of a constellation?
That's a good question. In fact, coverage is one of the key performance indicators of a constellation. Before defining coverage, we need to do a step back and define minimum elevation angle, because the minimum elevation angle is the angle from the local horizon of the RF transmitter till the center of the cluster of spacecraft, and this angle affects the coverages. The lowest the elevation, the better is the coverage. This angle also has an impact on link budget. The lowest the angle, the more stronger it needs to be the transmitter to be detected, so the signal to noise ratio is lower. So let's assume a conservative value of 30 degrees for the elevation angle, and given the constellation we are flying, so KSM is flying, Kleos Scouting Mission 1 is flying a 37-degree inclined orbit. Thanks to the elevation angle we defined, we can cover up to plus minus 45 degrees latitude, roughly. For KSF, so the Kleos Scouting Follow-on mission, which is flying a synchronous orbit, so a polar orbit, we can cover the full spectrum of latitudes.
Okay, so can you tell us maybe some examples of some areas of interest that are covered by both constellations?
Sure. So for KSM, which is the lowest latitude coverage cluster we have, we can cover the Mediterranean Sea, the Mexican Gulf, the upper part of the Chilean coast, and also South China Sea. With KSF, we can expand this coverage from the Arctic Sea, so also the Baltic Sea as well, to the Antarctic Sea, having a look also to the coast in Australia and the full Chilean coast.
That's really interesting, because some areas like the South China Sea are suffering from overfishing activities. So basically the users are interested to monitor those kind of regions. And speaking about users, so one of the key performances are, let's say, coverage by the constellation, but there is also another key performance metric, which is how often does the constellation visit a given area of interest per day. So we're talking about the number of daily accesses for a given constellation. So can you give us a little bit more details about what Kleos constellation can achieve as number of daily accesses? And before that, maybe how you define that?
Sure. This is a very complex question to answer to. For sure, I can tell you that the access number per day is a very important parameter in evaluating the performance of a constellation. The number of daily accesses, it means the number of accesses our clusters have to an area of interest each day. This needs to be averaged over a year because of seasons and because of orbital geometry, so it's not always constant. So it's a very tricky answer to because there is an orbit geometry standpoint. So we need to consider the relative position between the area of interest and the orbit. But also there is also the standpoint of the operations. So in case of multiple area of interests access sequential, we need to have the system, so the space system, to support the multiple acquisition, but also the relative distance between the area of interest and the ground station, because we want to provide the customer updated data. So the numbers I'm going to show you are just taking into account the orbital point of view. So considering the geometry of KSM and KSF, so the full constellation, above the equator between 0 degree and 30 degrees, we are covering an area of interest 3 times per day.
Okay.
Then the area of interest axis reaches a plateau,
Okay.
and then above 50 degrees is slightly increased up to 75 degrees, where KSF, being polar, really enhanced the number of axes per day. So we can speak about 7 times per day above 75 degrees latitude.
Okay, thank you. Thank you for all these insights. So basically, we're able to make 7 daily axes of the constellation. So basically, these key numbers are related only to KSM and KSF constellation. But since we are planning to put more constellations on space, the number of daily axes will increase, right?
Yes, exactly. So the number of cluster flying the orbit is a key parameter. And currently we have 2, but we're planning to send 20. And this will indeed increase the number of accesses per area of interest and reducing the revisit time, so the time between the accesses, consecutive accesses.
All right. So one final question that is going to link maybe your background as a systems engineer to my background in signal processing. One of the key factors that is going to affect the geolocation accuracy is the cluster geometry. So the way how the spacecraft are spread above a given area of interest would impact the geolocation accuracy. And since in Kleos we are optimizing the geometry over key areas of interest, I'm interested to know what is the optimized geometry, how it looks like, and also how do we achieve that?
That's a very important question. We can say that there are multiple solutions to the question you're saying in terms of optimized geometry. Currently, in KSM-1, we're flying an optimized geometry with 4 spacecraft divided in 2 orbital planes, meaning that 2 different orbits shift in right ascension of ascending node of a very small amount in degree, not in inclination. And inside the orbit, each spacecraft is unphased of a very small aperture in true anomaly. So the difference in position of the spacecraft in each orbit is obviously the same.
Yep.
And the center point of the distance between one satellite and the other inside the same orbit, projected into the other orbit, is occupied by one of the 2 satellites.
Okay.
So by this we can build what we call the diamond-shaped formation. And as you said, there are multiple challenges we encountered post-launch. Yeah. So one is, how can we build it up? It's not that simple, because the launcher releases you with a few minutes in time difference, all 4 spacecraft in time delay. Yeah. So what we need to do is to move basically from the same point to a different formation.
Okay.
And this is a challenge. The second challenge is to maintain it. So when you're there, as you know, the space environment is perturbed. There is the sun, there is the atmospheric drag, and also the mass of the Earth not being distributed equally provides a source of perturbation. So even a small difference in altitude, for example, provides an unphasing of the spacecraft. So we need to maintain carefully the formation when we're there. To solve both issues, what we have and what we fly is a propulsion system. So with propulsion we can control the spacecraft, maneuver, and put them where they need to be.
Okay. I retain from your answer is that there are 2 basically major steps. The first one is to get that diamond shape once the spacecraft are launched, and the second step is maintaining them over the lifespan of the mission. Also, what we can retain maybe is that it's true that it's challenging to build satellites and launching them to space, but it's also challenging to basically maintain the same quality of service during the lifespan due to the different perturbations that occur in space.
Exactly.
Thank you very much for all these insightful information, Federico.
You're welcome, Rami. It was a pleasure to be here.
Thank you.